The last problem we solved for the maximum height and the maximum range of a projectile that was starting from the origin. This time we're going to do the same thing, except for the projectile will be starting at some initial height, and we're going to call that y naught. And in the packet, I asked you guys to first solve it with actual numbers plugged in before you do the letters, because it's easier to get a feel for it that way. Especially because this equation turns out to be quite messy and it's not very reducible. But I mean, you could just go right into the letters. That works perfectly fine too, and that's what I'm going to do here. I'm not going to do the actual numbered problems. So the first step is to find the height, and intuition says that this maximum height really is only going to be shifted up by a factor of this y naught here. Nothing really significant is going to change. See if you can make sense of that intuition before we get into the math. Sometimes it helps to like get an idea of where you're going before you actually get there, so you can make sure that your answer makes sense. But either way, we'll certainly prove it with the math, and we'll use the same equations, and we'll say delta y equals negative 1/2 gt squared plus v naught sine theta times time. But what do we know about delta y? We know delta y from the definition of delta, meaning change in, which means that our y minus our initial position. And that's what delta y is. And so this time, since normally we say delta y, we use delta y interchangeably with just y, because more often than not, y naught is going to be 0 in a problem like this. But in this case, y naught is not 0, so we can't allow that. So if we solve for y, we're going to get y equals negative 1/2 gt squared plus v naught sine theta times time plus our initial y position. And so it has changed our y equation in some way, but we still want to do the same thing where we'll solve for when our vertical velocity is equal to 0. And that's not going to be impacted by the fact that there's an initial position, because position has no impact on the velocity equation, which is going to be velocity in the vertical direction is equal to negative gt plus v naught sine theta. Setting this equal to 0 like we did in the first one, because that's when the ball or the projectile, whatever, is going to reach its maximum. And that yields gt equals v naught sine theta, and t equals v naught sine theta over g, sorry. And we're just going to plug that value of time in for time in our y equation here, one right there and one right there. And when we do that, we get y equals negative 1/2 g times v naught sine theta over g, that whole thing squared, plus v naught sine theta times, I'm running out of room, so I'm just going to write that all down here, plus v naught sine theta times v naught sine theta over g times, I'm sorry, not times, plus y naught. And I'm going to skip a little bit of the algebra right here, because I did it in the last video, and doesn't make, and if you're any questions about it, you can refer to that one. But after simplifying, we'll get y max equals v naught squared sine squared theta over 2g plus y naught. So the math again showed what our intuition suspected, and that was that the maximum height is simply going to be our last equation plus whatever our initial height was, and that makes sense. Now our range is going to be a bit of a different question, and the first thing we want to consider is, can we use the equation that we derived in the last one, and that was that our range is equal to v naught squared sine of 2 theta over g. So the question is, can we use this equation to figure out the horizontal range, which is going to be right here, this length, rather, that length? And the answer to that is no. And that's because our initial, one of the reasons why that worked in the last case was we took the delta y equation and we said delta y equal to 0. And we could do that in the first case, because when we were launching from the origin, where it landed, there was no change in its vertical displacement, only horizontal at that point. But in this case, the ball is starting at this height, but it's ending at this height. So our delta y isn't equal to negative... I'm sorry, our delta y isn't equal to 0. It's in fact, it has some value, and that value is going to be negative y naught. So in order to solve this, we're going to have to use a little bit more. We're going to use the same equation still, but this time when we're solving for t, we'll get a little bit more of a more complicated quadratic equation. So we're still going to use our equation delta x equals v naught cosine of theta times time. And this time I'm just going to skip. You guys understand where this y is coming from because it's the delta y. I'm just going to add the y to both sides, the y naught rather, and that's equal to negative 1/2 gt squared plus v naught sine theta t plus y naught. And this y we can safely set to 0 because this y is not. This y right here is not representative of the y right here. It's representative of when the overall y is equal to 0, and that's right here, which is what we wanted. And again, we have a quadratic when we set this equal to 0. And we can see that this time there will still be two solutions. One will be here, and the other one will be back here, in fact, at negative time. So again, it'll be pretty clear on which solution to choose because we have two. But we're going to pick the one that obviously is in the positive time, because we don't really care about what's happening to the projectile before we started throwing it, because it just doesn't make any sense. So if we want, in order to solve this, there's nothing, we can't factor out t like we did last time or anything like that. What I am going to do is I'm going to flip it so that the a term is positive, because that's, if we don't do that, the quadratic formula, which is what we're going to use, is going to produce an answer that doesn't make much sense. And that's something that you might want to try out in your spare time. Try using the quadratic formula with the equation just as it is and see how you get a nonsensical answer. And that's just an example of how sometimes we have to be careful of what we do with math. And then even that, if we do all the math right, sometimes there are little minutiae that make our equations turn out to be false. And it's always important to have an intuition of what kind of answer you're expecting so we can catch those mistakes and we can correct them. So all I'm going to do is I'm going to multiply all three terms by -1. So I get 0 equals 1/2 gt squared minus v naught sine theta t minus y naught. And again, I'm going to be solving for t, so I can plug it into our delta x and therefore get a value for the horizontal range. So let's do that now. So quadratic formula, t equals -b. So b will be played by the role of negative v naught sine theta. I'll do that in a different color so it's more clear. So b will be played by negative v naught sine theta. A will be played by 1/2 g. And c will be played by negative y naught. So t equals -b, so that's going to be positive v naught sine theta plus or minus the square root of b squared, because remember a negative times a negative is going to be positive, so this will be positive, v naught squared sine squared theta minus 4 times a, 1/2 g, times c, negative y naught. That whole thing divided by 2a, I'll save a little bit of room, which will be 2 times 1/2 g, and that's our solution. Now, before we start simplifying, I want to eliminate the nonsensical root. And the way we can, there's a couple ways to think about it. One is to assume that we want the positive root because the answer is the value of time that's more in the positive direction. We can see that right here. If we take the negative one, it'll bring us more into a negative, which will bring us over here, which is not good. Another way we can see it is, if we plug in 0 for y naught, we should get the same value of t that we found in the last one, which was 2 v naught sine theta over g. And if you plug in 0 for y naught here, and you take the minus, you'll end up getting 0, because you'll have v naught sine theta minus v naught sine theta, because the square root of v naught squared sine squared theta is v naught sine theta. So you'll get 0. But if you take the positive, you'll get the 2 v naught sine theta over g, which is what we expect. And if you don't believe me on that, try it out yourself. Plug in 0 over here, and try out both roots and see how they match the ones that we found in the last video. Useful thing to try. So you can pause the video right here and give it a try before you go on. And so now I'm just going to simplify, and we get t equals v naught sine theta plus, because remember we've decided that I'm taking the positive root, plus the square root of v naught squared sine squared theta minus, rather plus, because we have a negative times a negative, plus, and 4 times a half is 2. So plus 2g y naught d all over 2 times 1/2 g, which is just g. And so this is our value of time that we want to plug into here, into our delta x equation. And I know it looks messy, and we wish that there were an easy way to simplify it and make it look prettier. But sometimes in mathematics, things work out to be nice, beautiful, simple little equations. And sometimes in mathematics, things turn out to be ugly, messy, stinky, long equations. But such is life, and we've got to deal with that. So plugging that into our delta x equation, we get delta x equals v naught cosine theta. Well, I don't need the parentheses. You guys get the idea. V naught cosine theta times time, which is this whole huge quantity right here, times v naught sine theta plus the square root of v naught squared sine squared theta plus 2g y naught all over g. And we can simplify this a little bit by multiplying the terms out, and we get delta x equals v naught squared cosine theta sine theta I'm gonna leave the g, make the whole thing over g. But you could separate the g into each individual terms. That's something your call. It really doesn't make a difference. Plus, I'm going to put the v naught cosine theta into the square root. So plus the square root. So in order to do that, I have to square it. And this is a little algebraic trick. Plus the square root of cosine v naught squared cosine squared theta. And we can do this because it's the same thing as we can factor this out, and we would just be left with the v naught cosine theta, which is, so we're keeping it equal, times v naught squared sine squared theta plus 2g y naught. Again, that whole thing over g. We get delta x equals v naught squared cosine theta sine theta plus the square root of, I'm going to distribute the v naught squared cosine squared theta now. And so we'll get v naught to the 4th times cosine squared theta sine squared theta plus 2 v naught squared cosine squared theta times g times y naught. And all of that divided by g. And so we are getting messier and messier. But I'm going to do, I could be done here. You could count this. But I want to make it as similar to the last problem as possible. So we can see how so it makes it easier to see, especially how if y naught is 0, it quickly becomes what we saw in the last video. And in order to do that, I'm going to, remember last time we said that sine of 2 theta is equal to 2 cosine theta sine theta. So then it makes sense that 1/2 sine of 2 theta, I'm just going to divide both sides by 2, is equal to cosine theta sine theta. Right? And also, I'm going to do another little trick. 1/4 sine squared of 2 theta is equal to cosine squared of theta sine squared of theta. And so I'm just going to make those substitutions in. The cosine squared sine squared will be in here. The regular cosine theta sine theta will be right here. And so we can see that now. Delta x equals v naught squared, or rather 1/2 v naught squared sine of 2 theta plus square root of v naught to the 4th, or I'll write the 1/4 in front. 1/4 times v naught to the 4th sine squared of 2 theta. And this I'm just going to leave as is. Plus 2 v naught squared cosine squared theta times g times y naught. And all of that divided by g. Now, I'm gonna leave it there. You could do a couple more things. Like, for example, I could factor out this 1/4, turn that into an 8, so I could pull a 1/2 out, and then factor that, and then put that all over 2g. If you guys can see how I would do that. You know what? I'll do that. So I'm gonna pull this 1/4 out, and in order to do that, I'm gonna have to multiply this by 4 if I'm pulling a 1/4 out of that. And so if I do that, I'll be pulling a 1/4 out from this whole thing, which will mean that I'll have to multiply this part by 4, which will leave me 8. And when I pull the 1/4 out, it's going to become 1/2. And then both these 1/2s can pop down to the denominator. So we'll get delta x equals v naught squared sine of 2 theta plus the square root of v naught to the 4th times the sine squared of 2 theta plus 8 v naught squared cosine squared theta, that's a theta, trust me, times g times y naught, and all of that divided by 2g. Now, if you did this problem by yourself and you're just watching the video to check your answer and you don't have exactly what I have here, that's probably because you reduced in a different manner than I did. There's plenty of ways to have reduced, and any number of them are perfectly fine. It's also possible that because this was such a lengthy algebraic problem that I made some simple mistake somewhere with a 2 instead of a 4, or I lost an exponent or something like that. And this just goes to show that, you know, before, I've already made this point, but I'll say it again, that before we had our nice little neat equations of delta y equals 1/2 sine squared theta over g, and our range is v naught squared times sine of 2 theta over g. But this equation, when you add in a y naught, it makes our range a lot more complicated to figure out. And another interesting question that I'm not going to do in this video, and I'm not going to, and I didn't ask on the packet, is what's the optimal angle to fire this at? And that's a bit of a hard question because it's going to involve taking the derivative of this whole expression with respect to theta and setting it equal to 0 and then solving for theta, and that's going to be very extremely complicated and a lengthy calculation to do. You are more than welcome to do it, and I would love to check your work and see how you did on it. And you'll see that if y naught is 0, your optimum angle of theta will be 45. But as y naught increases, or as y naught becomes into existence, the optimal angle that you should launch your projectile at changes. And it's cool that we can prove that mathematically. And so I hope you do decide to do that if you're up to the challenge, because it really is an interesting thing to attempt. And I hope you enjoyed this video. See you next time.